I'm Yifan from Beijing University of Post and Telecommunications. My topic is compatible branch coverage-driven symbolic fusion for efficient firefighting. In the realm of software development, bug detection is a critical task. Symbolic execution and power program analysis technique has been extensively used for this purpose. However, one of the main challenges it faces is the path exploration problem, which can lead to inefficient analysis. To address this, we have introduced a novel approach to symbolic fusion, known as compatible branch coverage driven, shortened CBC. To formally introduce the methods of this paper, we first present an observation made in this work. By analyzing a large number of programs, we observed that sometimes branch coverage is sufficient instead of path coverage. For example, consider a simple abstraction provided in our slides. Specifically, the current function of the A and B. For this program, this Symbolic application needs to install 4 paths to cover the program. However, through concrete analysis, find that the values of A and B, pi2 and pi3, are already covered by pi1 and pi4. Specifically, A and B only takes on the values of minus x and minus y. After exploring pi1 and pi4, while exploring pi2, the value of A as minus x is already covered by pi1, and the value of B as y is already covered by pi4. So the same logic applies to pi3. Therefore, for this program, it is only necessary to explore pi1 and pi4 from all cases. So, for the path exploration problem, our observation was that branch coverage is enough among branches that will never jointly find any program in. So, based on this insight, we proposed a solution that identifies cases where branch coverage is adequate and enforces branch coverage on them. Overall, our solution encompasses static and dependence analysis, the identification of compatible sets, and path-pruning in symbolic fusion. These techniques allow us to effectively reduce the number of paths that need to be explored, thereby enhancing the efficiency of symbolic fusion. Our approach begins with static dependence. In this phase, we define branch dependence and the branch dependence set. Firstly, branch dependence is a mapping that indicates whether a node has active or controlled on another node. The branch dependence set includes all nodes that have true dependence with for the given program shown in the figure. The right side is the graph. According to the definitions of data and dependence, we know that node 2 has a control dependence and node 3 has a data control dependence on node 12. According to the definition of branch dependence, we can determine that node 2 has a branch dependence on node 12. Furthermore, we can derive the branch dependence set. For example, for branch 2, it has a control dependence on node 3, and node has a branch dependence on the 12. So its BD set is 3, 12, 13, and 14. Similarly, we can obtain BD set branch 4 and branch 8. After branch dependent sets, we need to further refine and process them and divide it into the branches into the compatibility. Through this step, we can capture the dependencies if by identifying which branches are redundant. Firstly, if two branches are compatible once their branch dependencies on intersection and compatible Yifan, there are two equals to. By doing so, we can group the branches into different sets. We group pairs of compatible branches into a set and call it the compatible branch set. So it is the CBR set. For example, suppose we have n branches and using BD set information calculated through the line analysis. We can divide these branches into m disjoint CBR sets calling combination CBR set. There are no dependencies between branches within each set, so they are independent of each other. Therefore, we do not need to perform path coverage, but only need to perform branch coverage. Hence, CBR set is the main basis for our path-pruning. Overall, after our method divides the n branches into m CBR sets, the complexity of behavior coverage 2 to the n. For the previous example, the program has 3 branches in total, and we have already obtained the expected BD sets. We can partition the branches into compatible sets based on each branch's BD set, and shown in the figure on the right. Since BR4 and BR8 do not have branch dependencies, so they can be placed in the same form set. However, BR2 has dependencies in other branches, so it cannot be grouped with them. After the partition, we obtain a set where BR4 and BR8 are grouped into one set, and BR2 is grouped into another. Finally, we will use the partitioned compatible branch sets to guide the path exploration in symbolic calculation, effectively pruning redundant paths. Since each CBR set contains branches that are mutually independent, the behavior coverage for each CBR set requires at most 2 passes. For example, path 1 covers branches where conditions are true, and path 2 covers all branches where conditions are false. In fact, we show each CBR set as a super branch. Using the path coverage problem for each set, 5 branches to branch coverage problem. This is a major reason why the state space in symbolic solution is used. Furthermore, we are not limited to just path 1 and path 2 covering all pointers by handling all conditions true or false. Instead, the union of these 2 passes can cover all possible branch from each CBR set. For example, for the execution tree of the previous program, a traditional symbolic exploration strategy would require exploring 8 paths. However, we have obtained the CBR set and knowing that branch 4 and branch 8 belong to the same compatible branch set. With our CBC method, 1 by 2 is reached. It is determined to be redundant because branch 4 and branch 8 values differ. Similarly, path 3 and path 6 and path 7 would be redundant paths and to be deleted. So, it only requires exploring 4 paths. We have proven that function compatibility. If a fault can be detected with a specific depth bound under traditional Spark execution, it would also be detected. Further details can be found in the reference. Our CBC's implementation is built on top of and DG for C and C++ program. We have compared CBC with D, DGIC, and Joker on various benchmarks. KLEE is a classical tool for symbolic computation. DGIC is the most closely related to C, and Chopper is an extension of KLEE that performs well in vulnerable. Specifically, we select as a Coreutils than one benchmarks. To compare Catholic sensitivity, we designed 3 sample experiments focusing on aspects such as correctness, and efficiency. In terms of correctness, in SIR, that's one benchmark, they successfully identified and reproduced all bugs detected by KLEE, and in certain cases, even detected bugs that KLEE made. In terms of effectiveness, in the SIR and Intel's benchmarks, SIR achieved an average reduction of 50% in passing and a significant reduction in destruction. We found that as exploration time increased, CBC demonstrated a compared. This illustrates CBC's ability to delve deeper into the operation. In terms of efficiency, CBC achieved a very speedup of 3 times in the and 13 times in the least-than-1 benchmarks. However, CBC also introduced some overheads, such as purchase with more memory than KLEE. In some test programs, CBC even consumed less memory than KLEE. In conclusion, CBC is an efficient and sound approach to symbolic computation. The novel strategy based on program dependency analysis. It has achieved significant path-pruning and noticeable time reduction, allowing for quicker bug action compared to conventional tools, always achieving higher branch coverage in less time. Thank you for all your